So everything that we've talked about with quantum numbers leads to the Pauli exclusion principle, which states that no two electrons in an atom can have the same four quantum numbers. So at least one out of the four quantum numbers must be different. This means this has two major implications. The first of which is that there cannot be more than two electrons per orbital. The second implication is that if there are two electrons in the same orbital, they have to have opposite spins. So their m sub s values have to be opposite, minus and plus 1/2. So we can use this principle to do problems related to quantum numbers. Um, let's do an example problem of the sort that you'll have to do on the chapter 2 homework. How many electrons can reside in the 2p sublevel? So when you're asked a question like this, it's kind of implied that you're looking for the maximum number of electrons that are possible in that sublevel that you're talking about. So we have to kind of break down what 2p means. 2p, the 2 means that n equals 2. The p means that L equals 1. So if L equals 1, a consequence of that is that the multiplicity is negative, the multiplicity is 2L plus 1, or 3. The number of m sub L values tells us that there are 3 orbitals. So we kind of know this. We talked about orbital shapes, right, in 3 dimensions. 2p can be lying along the x-axis, the y-axis, or the z-axis. So we're just basically kind of using quantum numbers to prove to ourselves that there are 3 degenerate 2p orbitals for this, n equals 2 principal quantum level. Now, we know that each orbital can house 2 electrons. Therefore, the total number of electrons in a 2p sublevel is going to be 6, right? Because I have 3 orbitals times 2 electrons in each. So that's kind of how you think about problems like this. Let's ask a question in a slightly different manner. Can you tell me how many orbitals? Notice I'm asking about orbitals this time instead of electrons. How many orbitals can have n equals 2 in an atom? So that's a good question. If n equals 2, what are the possible values of L? So L can take values starting with 0 and going up to n minus 1. So if n equals 2, L can be 0 or 1. If L equals 0, then m sub L can only be 0. And if L equals 1, then m sub L could take 3 possible values, minus 1, 0, or 1. So the fact that there's only one orbital here, one value for m sub L, means that there's one orbital. The fact that there are 3 values of m sub L here means that there are 3 orbitals. If I add those together, I get 4 total orbitals. 4 total orbitals. And that makes sense for n equals 2 because we have the 2s orbital, the 2px, 2py, and 2pz. So the answer here would be that there are 4 total orbitals that can have n equals 2 in an atom, and these are their designations. Of course, each of them can house 2 electrons, so you could house 8 electrons total in the n equals 2 principal quantum level. All right, let's do one more example problem with quantum numbers. On your homework, you're going to have to do a couple of problems that might relate to this one. So, which orbital designations below are impossible? So sometimes you'll see an orbital designation that is quantum mechanically disallowed. So this is just an exercise in seeing what is a legitimate orbital and what isn't. Okay, I'm going to give you a list. 1p, 1s, 7d, 9s, 3f, 4f, 2d. Okay, these are just kind of random. So you have to kind of unpack each of these orbital designations and see which ones kind of have a lie in them, built into them. So let's start with 1p. This is saying that n equals 1, and this is saying that L equals 1. Now, those two things cannot simultaneously be true because the maximum value that L can take is n minus 1. So if n equals 1, L can only be 0. So we can see right away that this orbital designation is not allowed. It's not legit. Let's compare that with this one. Here I have n equals 1 and S means that L equals 0. That one's fine, right? If n equals 1, L can be 0. For 7D, n equals 7. D means that L equals 2. And that's allowed, right? Because if n equals 7, then L could be 0, 1, 2, 3, 4, 5, or 6. So 7D is legit. Let's look at 9S. 9 means that n equals 9. S means that L equals 0. That's okay. If n equals 9, then L can be 0, 1, 2, 3, 4, 5, 6, 7, or 8. For 3F, n equals 3. F is L equals 3. Once again, for the same reason that 1p was impossible, this is not possible. Because if n equals 3, the highest value L can take is 2. So 3F is not legitimate. For 4F, that means that n equals 4. F means that L equals 3. That's okay, right? Because 3 is n minus 1 in this case, so that's okay. That's allowed. Let's look at 2D finally. 2 means n equals 2. D means that L equals 2. Can that be? Absolutely not. N cannot be equal to L. L can only go up to n minus 1. So out of all of these orbital designations, we found 3 of them that are impossible.